So I need the straight line, which we call geodesic for a curved space. This is the one. Now we're defining it as the shortest path. So what do you mean by the shortest path? So the one gamma that minimizes L of gamma, which is the integral this integral, right? Or that integral, whatever you like. So the square root of, for the sphere here, it's the square root of cosine square phi theta dot square. I'm using this definition. Okay, so I'm using with the dots. You can use this, but that's fine. Plus phi dot square dt, okay? Can you determine gamma curve? So gamma has two components, phi and theta. Phi of t and theta of t. Phi is a function of time, theta is a function of time. Can you determine phi as a function of time, theta a function of time that minimize this integral? Can you do that? What type of problem is this? It's a calculus of variations problem. So actually, because our objective function or the integral has a square root, it's not that nice. So the minimization of this guy is equivalent to minimization of the energy of the curve. I will simply just remove the square root, okay, to make the problem nice. And I can do that because I know that this is always positive, so that's fine. I can square it to make the problem nicer. Now it's convex and better. So indeed, this is a calculus of variations problem, and you should be able to solve it without knowing any of what I said from before. How do you solve this problem? If I told you find gamma that minimizes this integral, how do you solve it?
Take the function.
This integrand, whatever you want to call it, let's call it say Lagrangian or whatever, right? And what we do?
First variation.
It's d by dt. So the first variation, thank you, this is great. The first variation of E is 0, gives you d by dt partial L partial the first coordinate dot minus partial L partial the first coordinate, and the same for the second, right? Any question about that? So what you will get from here, this is straightforward. If you substitute there, you will get d by dt cosine squared phi theta dot 0 d by dt phi dot, which is phi double dot plus sine cosine theta dot squared is 0. These are the two equations governing what? These are the two equations governing what? If you solve these two equations, first of all, if you solve these two equations, I'll get phi as a function of time, theta as a function of time. What do they represent?
It's a parametric equation for a line, or a straight line on the curve.
Exactly. These are just give you the curve. What's that curve? It's the one that minimizes the distance. This is the straight line from a point of view of minimizing distance. Okay? How do you compare this set of equations to that set of equations? These are the equations of motion. We derived them from Lagrangian mechanics. Has nothing to do with geometry. Here, we are just working on the sphere. We have nothing to do with mechanics. We started, well, I have a sphere, and I want to determine the curve on the sphere that minimizes the distance between the 2 points, right? It turns out to be a calculus of variations problem. That's fine. Luckily, we knew how to solve it, and we got equations governing that curve that minimize the distance. It turns out that these equations is exactly the same as these two equations coming from dynamics, correct? So again, that notion that the trajectories of a free particle, indeed they follow a straight line. This line can be defined as a curve with zero acceleration or a curve that results in minimum distance, right? Shortest path. Any question about that? Any question? Yes, Joseph?
And these two are equivalent, is this for any manifold?
This is very good. We're going to talk about this in a minute. Very, very good question. Yes?
Can you please explain again why that square root of that is equals to the s?
Oh, this is a good question. So the length is equal to that. Any question about it? Okay. Now this is the length of a curve. The length by definition is the integral of the d length, the ds, the d line element. Right? So I'm saying we have a curve like this. The length is the integral of ds. Right? The line element, yeah. So I'm saying by definition the length of any curve is the integral of ds. So by now comparison, before that they were not equivalent. Now I'm making that equivalence because I derived that length of gamma is equal to this, and I know that length of any gamma should be the integral of some ds. So now I compare to get what my ds is equal to. Okay? My line element. So as far as computations are concerned, if you are given any shape in 3 dimensions or whatever, any shape, can you compute its Riemannian metric G? This is one of the, perhaps you have already seen it in your home. Okay, so coming back to Joseph's question. We have a covariant derivative from last time, a way that by which we make differentiation on a manifold. We make differentiation here versus Riemannian metric. What's the Riemannian metric? It's a way that we can do dot product on a manifold. How we do computations here, or how this is completely defined. The differentiation is completely defined by these Christoffel symbols, right? If you give me gamma ijk, I know immediately how to differentiate any vector with respect to another from the formula that we had last time. So this guy is completely defined by the gamma ijk. This guy is completely defined by the matrix, right? So give me any, what's this? This is n, right? Because k runs from 1 to n. This is n matrices. If you give me any n matrices smooth, right, to be smooth, satisfy some conditions, it tells you a means of doing differentiation on the manifold. One way of doing it. Likewise over there, if you give me just a smooth matrix that is symmetric and positive definite, these are simply the conditions. The conditions over there are more complicated, we'll not discuss. Symmetric and positive definite. So I can come up with infinitely many of those. Well, each one defines a way of doing dot product, right? That's fine. Now, from this perspective, I can define the straight line. Call it geodesic, whatever. From this perspective, what is the geodesic? From this perspective,
Acceleration is 0.
Zero acceleration, a curve with zero acceleration. And how do you compute it? Well, it's nabla gamma dot is 0, a curve that's satisfying this equation. From this perspective, what is the geodesic? Shortest path. So gamma that minimizes L of gamma integration of square root g of gamma dot and gamma dot dt, right? And if you want to make it a bit easier, then it's the energy of the curve because they are really equivalent. The minimization of this problem is equivalent to minimization of that problem. So the curve gamma that minimizes this guy, okay? So like I said, give me any symmetric positive definite matrix. I'm going to do this and minimize here. So I'm going to get a geodesic. Actually, we call it, this is why we call it a geodesic of this Riemannian matrix. Okay? Because it really comes from here. And the same here, we call this a geodesic of this covariant derivative. Okay? But if they are equivalent, if this covariant derivative and the Riemannian metric are compatible, and in this single lecture, of course, we are not concerned with any other types but the two that are compatible with each other. Now, when G are compatible, we can intuitively expect that they have the same geodesics, right?
This means that all the G matrices which we are going to form, they all will be compatible with the same covariant matrix.
No, not all of them.
Not
all of them.
Some
So
of them.
in particular, when you start with the standard, because I start with the ds squared, right, which is dx squared plus dt squared, right? I can start with this s squared equals maybe 4